BSides DC would like to thank all of our sponsors, and a special thank you to all of our speakers, volunteers, and organizers.
About 6 months ago, I was in San Diego and I was talking to one of the lead nuclear core simulation engineers in the world, and I was kind of telling him about some of these different SCADA vulnerabilities that we've been finding, industrial control issues, and he said something to me that made my jaw drop. So I'm a reverse engineer at heart. My whole life in general has been about taking things apart, trying to understand them, and I got into this security industry by realizing that I can get paid by doing that, trying to find problems. But this nuclear engineer was kind of telling me about fault tolerance in these systems, about failure modes in current nuclear reactors in the US. And what I took away from talking to him was that we're on the edge of a cliff, that having designed a lot of these systems decades ago without any real consideration of a network-based attacker, without any thought really toward a network attack surface. So it leaves a big opportunity for disruption and destruction from a remote attacker who you won't even really see coming. So last year, Tenable research found more than a dozen critical vulnerabilities in different SCADA software and hardware, and they're critical vulnerabilities because they provide unauthenticated or pre-auth remote code execution in the affected systems. A lot of these vulnerabilities were found by our vulnerability detection team. If you're familiar with Tenable, they make Nessus, and the vulnerability detection team basically writes exploits for Nessus to check corporate networks. So this team basically in their daily work looking at trying to exploit existing vulnerabilities typically come across new ones as well. So shout out to Tenable's VD team. And then another one that's not even on this list, a more newer one, there's one from Advantech, I think, web access, remote code execution, unauthenticated, and there's at least 3 other vendors that are currently in disclosure. So these things are always coming out. They're relatively easy to find for some reason, but yes, I guess I probably should. Does anyone use CodeSys? How about what's the other one? Schneider Electric hardware, FLM, FlexNet. So I guess I won't tell you guys what the vulnerability is in those since it's still in disclosure, but it's unauthenticated RCE. So anyways, let's move on. In this talk, I'm not going to just talk about all these vulnerabilities. I'll talk about 4 of them and kind of go into a little bit of detail about them. And then we'll look at an actual attack vector, and then we'll blow up a nuclear power plant. All right, so first one, Siemens. Siemens Step 7 has been around for a long time. It was recently rebranded a couple years ago as TIA Portal, TIA, Totally Integrated Automation Portal. It's used in all aspects of ICS development and operation, from the design phase to implementation all the way down to operation. Now, TIA Portal has a suite of simulation tools which are used in design as they're creating the functional flow of the operation. It has diagnostics and telemetry, which is used in data collection and production, as well as energy management. It's used in operation. So it's built for engineers, for integrators, as well as the operator personnel. Now, the vulnerability that we found in the software exists in the authentication package in the node server of TIA Portal. So TIA Portal implements functionality for authenticating web users and admins over SSL. After authentication, the session is switched over to WebSockets, but they don't use the login token generated in authentication in the WebSockets handling. So the vulnerability exists that you can just skip authentication and start sending WebSockets commands directly to the server. And of course, all administrator functionality is included in the WebSockets protocol. So you can do a number of things with this. An attacker could, for instance, modify user permissions, or they could create new users or administrators using that vulnerability, or they could just change application proxy settings to collect system information. But really the best thing that you could do with this is just to start a firmware update. And in the firmware update, you can specify the firmware server. So anyone on the network can just tell TIA Portal to run an arbitrary executable. So I guess, I don't know, is this good or bad? Like, maybe it's a feature. And I'd stress again that this software is currently used in production all over the US in critical operations. All right, the second one. So Schneider Electric, they make Indusoft Web Studio. And earlier this year, we found that Indusoft has several vulnerabilities, including this one. So this one allows an attacker to send unauthenticated commands to the application and leverage this vulnerability in command processing. So the command 66 message is able to be sent by an unauthenticated attacker. And it's used to specify to the server a database configuration update, to tell it to update its configuration. The update can be queued from an arbitrarily controlled server, similar to the Siemens vulnerability, and then the file sent back by the controlled server can execute operating system commands. And it happens because the developers overlooked a functionality in the Indusoft markup language to where it processes these bracket commands and runs them at in an administrator shell. And we have a proof of concept of this. Actually, all of these vulnerabilities have proof of concepts on Tenable's GitHub repository. And basically, there's some Python code, and it spawns an SMB server, uses the vulnerability to request the Indusoft Web Studio server to connect to our controlled SMB server, sends a malicious configuration update file, and runs calculator. Okay, third one. Here's another one from Schneider Electric, this one in hardware. So Modicon Quantum is a family of PLCs, and they're produced by Schneider. They're designed to be modular, and so they're interchangeable in the housing. They all have separate and modular functionality. Depending on the needs of the application, you can swap them in, put in different configurations. And one of the vulnerabilities that we found in the Modicon Quantum was an authentication bypass in the communications module, which would allow an attacker to administer the device without credentials. So the exploit for this one is also on the GitHub. It's pretty easy. It's like, a couple lines of Python. So it's just an example that, 0-day in ICS is not particularly difficult. So you literally just make a GET request to this hidden services API, and it resets the administer password and to a known default state so you can administer the device. All right, last one. Rockwell Automation. So they make software called RS Links, and RS Links Classic implements Ethernet IP, which encapsulates common industrial protocol, aka SIP messages. The packet has a 24-byte header, followed by command-specific data. So the packet header is, in it lists the command type, as well as the length of the data, but the application doesn't validate the command data length. So it allows a user to overflow the stack. The vulnerability exists in the connection path parsing functionality of Rockwell, and it's triggered by an extra long connection path. So the functions in this engine.dll library, which parses a connection path to extract a port and stores it in a buffer on the stack. The attacker, so the address of the buffer is about 200 bytes above the return address, but the attacker can actually specify up to 256 bytes, allowing you to overflow the stack and control return address. And the proof of concept for this is also on our POC on GitHub. All right, cool. So hopefully that wasn't too boring. Now let's look at the fun part. This is the application of some of these vulnerabilities in a theoretical attack on a nuclear power plant. So first things first, I'm going to turn you guys into nuclear physicists in 1 minute. Ready? All right. So nuclear fission is a process where a large nucleus splits into two smaller nuclei with the release of energy. And uranium-235 splits into krypton and barium. And in doing that, releases 3 more neutrons. And each of those neutrons can then go ahead and split another uranium nuclei. And uranium-235 That's the really nice isotope of uranium. 238 is the naturally occurring one. So when you're talking about enriching uranium, you're making the fuel have more of this 235, which better sustains a chain reaction. And weapons grade uranium is usually around like 90%. Nuclear fuel, enriched fuel, is usually around like 10% or so. So remember these neutrons that get produced, because those are critical for how the chain reaction is controlled. Okay, so we know that the fission reaction creates heat. The heat is used to make water boil and create steam, and the steam turns a turbine to make power. And that's it. 1 minute, you're experts, right? I don't even know why they teach nuclear engineering in school. You can just Google it. Wait, there's not any nuclear engineers in here, right?
Not yet.
Okay. All right, so now let's name the key players in the fission reaction, or in the nuclear reactor. First one is the fuel. So that's the uranium. It releases heat. It's the key element of fission. Second guy is the moderator. So that player slows down the fission reaction by absorbing neutrons. Every single neutron that he blocks stops another fuel nucleus from splitting. Third one is the coolant. So that guy takes the energy away from the core, and for our purpose, energy and heat are interchangeable. So the heat is synonymous with energy. Fourth one is the control. So those are the referees of the game. There's usually 2 of them. And when it starts to get out of control, the referees stop in, they can instantly stop the game. Cadmium, hafnium, boron, all of those materials absorb massive amounts of neutrons. So they have the power to completely stop fission. All right, so now that we understand nuclear fission, let's talk about some of the reactor designs. I'm going to describe 5 different nuclear reactor designs, each of which is more vulnerable than the last. So first off, and by far the most prevalent reactor, is the PWR, pressurized water reactor. There's about 300 of them in the world. These are predominantly the ones used in the US, and there are more and more of them as time goes on. They're typically more expensive, but they're very stable. So they have negative reactivity coefficients, which means that the temperature of fuel and coolant have an inverse relationship with fission reactivity. And boiling water reactors are also worth mentioning. So these are the little sister of the pressurized water reactors, and they're very similar in design. The only difference is that there's no separate heat exchanger. So the steam is produced directly inside of the reactor chamber. And one of the larger BWRs is the Kashiwazaki Kariwa in Japan. And that one was constructed by Hitachi and General Electric. So here we have the control diagram from the NRC for the Japanese Kashiwazaki Kariwa BWR. Now, one interesting thing about this design is that everything is on the same network. The control systems, all of the instrumentation, all of the safety systems, they can all talk to each other. But don't worry, it's air-gapped. So you can see the fully computerized, computer-controlled separate response systems. The redundant safety systems. So the ECCS on the bottom left, that's the emergency core cooling system. It basically just sprays boric acid into the reactor. Remember, boron absorbs neutrons, so it kills fission. And then also the SCRAM, a little bit to the right of the ECCS. That is the control rod insertion. So it drops control rods that are also made of boron into the core to stop fission. Okay, third design. So Canada came up with their own modified design of the pressurized water reactor that we use in the US, called the CANDU. Instead of light water, it uses pressurized heavy water as a coolant and a moderator. So deuterium, which is a hydrogen isotope, already has that extra neutron that light water would have absorbed. So there's reduced neutron absorption, which makes it easier to sustain the chain reaction. And less active atoms are needed to continue the chain reaction. So because of that, natural unenriched uranium can be used. So the fuel cost is much lower. But the reduction in fuel cost comes with a safety cost. So the fission core is designed with positive void and fuel coefficients. And that means that an attacker with modification access to control and safety systems can create a situation in the core where the fission reaction can run with disastrous consequences. Now let's talk about some of the safety systems in the pressurized heavy water reactor, the CANDU design. So here's a schematic of the Canadian reactor in Darlington, Canada. This information is from the US NRC also, and the ONRR, Office of Nuclear Regulatory Research, publishes all of this information at the NRC. So the CANDU system relies on computer control through 2 redundant computers that manage information and alarms. They implement redundancy, and they also have these, what they call diversification requirements. So they understand that the fission reaction is very temperamental, and so that these safety systems are critically important. So the 2 critical safety systems are required to be diverse. They have to use different operating systems. They have to use different architectures. They have to use different processors, hardware, and software languages. So for instance, one runs on Windows, the other one has to run on Linux. If one is using Intel processors, the other one has to use AMD. If one of the software is designed in Fortran, the other one has to be written in C++. Even so far as being developed, coded, and run by separate teams. So if you design for SDS1, you can't design on SDS2. Even if the logic and the functionality is all the same, it has to be completely different teams. So it's a great way to make the attack process a little bit harder. But in the end, all it means for us is that you need to burn a couple more 0 days. So just to give you an idea, Windows RCE, for example, sells for about 500K right now, and Linux RCE about 1 to 200K. All right, another design here. This is the AGR, Advanced Gas Reactor. And these are primarily used in the UK. They looked at this problem of liquid coolant boiling in the reactor and the issue of void coefficients, and they just said, let's remove that from the design. So in this case, the coolant is gas. You don't need to consider state changes of the coolant for stability. And then the final and the very best reactor is the infamous Russian reactor, same as the one that's used in Chernobyl. And it's extremely unstable. As liquid boils in the core, reactivity increases, causing a positive feedback loop. And in general, Russia has been phasing these out. There's only a couple of them left, like 2 or 3 or something like that. All right, so moving on. Now to the attack scenario. So our network will always be air-gapped as a precaution. And that means that we need to start with an initial infection just to get into an adjacent network. And that's easy to do with some type of phishing or some consumer-grade malware targeting an employee corporate network. And then once you're into an adjacent network, you need some human interaction or another propagation 0-day to allow us into the control network. There's a lot of different ways that this has been done. Stuxnet, for example, used a Windows vulnerability over USB and a man on the inside to jump the gap. And then once you're in the network, running on an operator panel or in one of the peripheral systems, the next step is to get onto a controller. And in this case, we can use another vulnerability, for example, the one that I was talking about earlier, the Siemens TIA portal, authentication bypass, to spread to the controller in the production network. And then after the infection phase of the attack's over, we need to start modifying control systems. So modifying PLC logic in production systems can be accomplished in a lot of different ways. The University of Tel Aviv at this last Black Hat talked about somatic controllers and modifying PLC logic on the fly. We've seen a lot of other stuff too, like the malware implant, for example, could just wrap the communications module and modify control flow for automatic function changes. But for our attack on the power plant, what we need to modify in the PLC is that we need to stop the coolant pumps from providing coolant to the reactor core. And we also need to be able to withdraw the control rods to increase the power of the fission reaction beyond criticality. And then a third and another integral part of the attack is delaying response by operators by providing some type of false telemetry and giving them the illusion of control over the reaction. So simulated logic could be implanted in the controller to send some types of calculated temperature, pressure, power readings to the operator interface. And then so as the plant operator attempts to move control rods up and down to slow fission reaction, the implant ends up sending simulated signals back to the operator to trick them into thinking that the reactor core is still operating under stable conditions. And then the last part of our attack on the power plant is just to disable the critical and the redundant manual and automatic safety measures. So the attacking malware can replace logic in the emergency core coolant system and the SCRAM control rod insertion such that they'll not trigger anymore from automatic or operator manual controls. And that would allow the core to heat, it would allow you time for the core to heat beyond the design limits and start the meltdown process. All right, so the Russian RBMK reactors are extremely unstable and they're still in use in a lot of places in Russia. So they rely entirely on these logical control systems to maintain stability. And so if an attacker were able to achieve control of the safety and control systems, they could very easily cause a catastrophic explosion within an hour. The Canadian PHWRs, pressurized heavy water reactors, are more stable than the RBMKs, but they're less stable than the light water reactors used in the US. So because they use unenriched uranium as fuel, their fission reactivity increases as fuel temperature increases. This would also allow an attacker to create conditions in the core for a runaway fission reaction and a resulting core thermal explosion. And all power plants in use in many countries, including the US, don't use these designs. They use light water reactors. So these types of reactors are designed to make it impossible to create a circumstance where the fission reaction would grow uncontrolled. So as the conditions of fission increase, reactivity always decreases. As water in the pressure enclosure boils, fission reaction slows down. As the fuel heats up, the reaction slows down. As the moderating water heats up, the reaction always slows down. However, there's always still the possibility of the core melting down. So an attacker would cause this by simply removing coolant flow from the reactor. And even as fission ends and there's no more chain reaction, the reaction byproducts are still decaying and releasing heat. So the reactor core is still heating up even though there's no fission happening. So eventually that would cause the fuel rods to melt and they'll melt through the surrounding enclosure, eventually ending in some type of thermal explosion and radiation release. So, this presentation is kind of based on fear and uncertainty, and I think nuclear technology in general evokes that uncertainty. So I wanted to just end it by saying, when I looked at it, in general, my impression is that nuclear power is very safe. It's really good. In the US, we get like 1/5 of our power or something from nuclear. And these light water reactor designs and safety systems are very robust. And I chose nuclear power as a vector because I thought it was interesting. But really, these vulnerabilities could be applied to any type of industrial control system, and they could still have the same types of disastrous results. So yeah, let me know if you guys have any questions. I'll hang around here and then afterwards. And then proof of concept for all the vulnerabilities that we found are on GitHub there. And feel free to contact me on Twitter. I'm available. Always like to talk about this stuff. And thank you guys for having me.
Any questions? Thanks. Hi. I'm wondering, it sounds like most of the exploits that you looked at were against the administrative interface or the GUI. Did you look at the underlying protocols that are often accompanying these, Modbus, BACnet, that kind of stuff?
Yeah, we've looked at those a little bit. You know, I think the tradition is that those are always very fragile. And, you know, in general, people are very afraid to patch, to upgrade, to scan those. But yeah, I think, you know, those have been seen often in vulnerabilities attacking hardware, because the hardware will in general rely on these protocols that don't have built-in authentication, don't have any type of encryption, so replay attacks are very common in those situations. Yeah, but these vulnerabilities were all, you know, there was only like 5 of them, 5 of the 19 or so that were against hardware that involved the actual hardware protocols.
Okay. One more question?
Yeah.
Nuclear is very sexy to talk about blowing up a nuclear power plant, but I think all of those vendors you listed are also used heavily in commercial operations, like our data centers for HVAC or power control and monitoring. Have you explored the risk associated to corporations for that?
Yeah, so not as much. You know, our group primarily focuses just on finding vulnerabilities, and SCADA and ICS and those types of technologies are really fun to look at because those implications that you talked about. But we don't, in general, don't look at, you know, what you could do with it. And so this is really the first time that we've explored what are the possibilities for, you know, what you could do with a vulnerability. So, you know, it might be interesting to look at some of the other vectors, and you know, I know that there are some government contractors that do look into that and do penetration testing against, you know, existing infrastructure.
Good morning.
Morning.
In your example, you gave a target that was air-gapped. So it does require quite some human element to get into it. Is that the norm in your research? And have you ever come across something in use commonly that doesn't really require a human element to attack?
Yeah, in general, you know, air gapping is kind of like the go-to method of, you know, it's almost like security by obscurity in a sense, to where you have a false element of protection, where, you know, it's one more step for the attacker. So we've seen it, I think, at least 3 or 4 times in the last decade of where, you know, threat actors or malware have found a way to do it. But to answer your question, I think in general, these industries across the board almost always do it. They have some type of segmentation, either, you know, software and hardware segmentation, or physical, you know, isolation like air gapping or something like that. So yeah, it's very, very, very common.
Good morning. I think kind of what the 2 prior questions to mine was alluding to is like also like that threat and vulnerability management portion of it, because these are some nasty vulnerabilities, right? But you just can't just scan these networks. So what do you recommend as some preventative measures against them being exploited on the network?
Yeah, you say you can't just scan them. I would counter that to say, really, you should. And you know, what you mentioned is a great thing, that you can't just scan them. 99% of the vendors that we talk to that implement this OT, that's the thing they say. They don't want to scan them because it works. You know, it's in operation. It's like the actual production environment. They don't want to scan it because when you do scan them, the things are so fragile, they just crash. So like Nessus, for example, I worked on Nessus for a long time, and you know, people don't use that to scan their OT because it's critical infrastructure, it's working, and Nessus can crash them. It sends exploits at them, and it like just kills the server sometimes. So, you know, that's a very good point that you bring up. And you know, there's a disconnect there between IT and OT, to where the OT people, they don't care as much about security, and IT people are yelling at them, say, fix your stuff, dude, you're vulnerable, you know. So as far as mitigations go, you know, I don't have a great answer for that. Like, I can just say there's a big disconnect there, and eventually, you know, something like this will happen in the next 5 or 10 years, and we'll be like, oh, okay, we should patch our OT. But, you know, mitigations are try and scan, you know, as best as you can. You can do it really fragilely without sending tons of data. You can just kind of like probe, look for versions, understand what you have on your network, and implement whitelisting, implement network segmentation. These are all things that are going to limit the attack surface, and just make it harder. In my opinion, you can't prevent zero-day. You can't prevent an attack from working, but you can make it harder. So you can make yourself the one that's not going to be the one that gets attacked. The lower bars will always get hit first. So.
Good morning. I have a question in regards to the Rockwell proof of concept. I was just wondering if there was any stack protection, memory randomization, or like dep protection, or possibly like an underlying SE Linux to mitigate the possibility of gaining remote code execution.
Yeah, that's a good question. Like, we can go back to the proof of concept. I think that one was on Windows, and the proof of concept ends up just crashing the process. So let's see. Siemens. Yeah, I know for sure that there are no stack cookies in this. It doesn't compile with stack protection. But on the other hand, I don't think that memory is randomized either. So. Yeah, so you can control return address. The exploit that we put on there is not a full remote code execution. It could be used for that, but we just didn't put in the extra, sometimes these things take like an extra, 20 hours of work. So this was enough to demonstrate exploitability, and we sent that to the vendor. But yeah, you don't see a lot of these exploit mitigations in these applications. A lot of them were written a long time ago, or just in general, the vendor doesn't really care about implementing these really easy security measures. It's a good question.
Talking about at-risk systems, related to that, anyone really doing research into transmission distribution systems for power? Because you can have an air-gapped network, but if you've got a chain link fence out in the field being your only defense, there's not really much going on there.
Yeah, I know for sure. I've talked to a couple different guys who are in that exact sector. Like, there are a handful of guys who do a lot of the government contracting for penetration testing these critical infrastructure in the U.S. And one of those is power plant lines. And I know that that was one vector that they looked at, how to access these systems through kind of like these side channel methods. So I don't know too much about it, but I know that there are people that look at it. Yeah.
Are there any other questions? No? Well, thank you very much, Joseph.